Alright, silly people, here's the situation. It's a cone um, that is rolling around on a table uh, with some. It makes one rotation um, in a time interval tau, right? Making an angle alpha with the surface, um, has a center of mass, a distance a away from the vertex, and we're meant to find the kinetic energy in terms of, you know, tau and the geometry of the cone. And then we're also meant to find the angular momentum uh, components, so Lx, Ly, and Lz. So, let's get to it. So, uh, the kinetic energy is going to have, right, it's going to have a um, translational term. So, 1/2 mass of the cone, linear velocity squared. It's also going to have some rotational terms. When we're talking about um, stuff in this chapter, you can just use this formula. So it's Ixx omega x squared, Iyy omega y squared over 2, Nizz omega z squared over 2. Right. Okay. Um, so let's deal with the mass first. Let's put it in terms of the density of the thing times the volume of the thing. And the volume of a cone like this is actually pi r squared h over 3. So it's looking like that. Sure. Um, so that's awesome. Uh, let's talk about the angular momentum vector. Right. So it's pointed along the axis of the cone because that's the direction that the cone is rotating. But the contact surface um, means that we can confine the angular momentum to have two components, either yx, yz, uh, or no, either omega x, omega z, or omega y, omega z. I'm going to choose x. Um, so omega is just omega x, 0 omega z. There's no y component really, because it's just kind of perpendicular to the whole situation. Um, so I'm going to rewrite the kinetic energy now as T equals rho pi r squared h v squared over 3, over 6 actually. And then we still have omega x, and we still have omega z. Don't know what those are yet in terms of the problem. Right. The angle between the contact surface of the cone and the axis of the cone was defined in the problem as being alpha, which means we can define the angular momentum vector as being some magnitude omega times sine alpha for the x, and then some magnitude omega times cosine alpha for the z. Okay. Cool. So the velocity of the center of mass, the linear velocity, we're talking about v, um, very simply is just the length it is away from the vertex times the rate at which the cone is going around so theta dot is what I'm calling it, times cosine alpha to get it up to that length. Um, so plugging that stuff in back to the kinetic energy, we're looking at rho pi r squared h a squared theta dot squared cosine squared alpha over 6 plus ixx omega squared sine squared alpha over 2, and then izz omega squared cos squared alpha over 2. All right. It'd be nice if those were equal, but they ain't. So now look at this. If you change your point of view in the problem, so change your inertial reference frame, and you're looking straight down the contact surface now. You're looking this way, and so the cone is like making a circle from there. So it kind of looks like at any particular point. It could be there, or there, or there. You're looking down the contact surface. And then A is this distance away from the contact surface. So that's A. It's A, the center of mass of the cone. And so the rate at which A moves around in that case is equal to the angular velocity. So you can also express V as you're just looking at omega A sine alpha. I'm going to say omega A sine alpha. That's a completely valid way to express V as well. And because we can do that, because we can represent it in those two different ways, we can set that equal to each other. So A theta dot cos alpha is equal to omega A sine alpha. And then now we know what omega is. Canceling out the A's, theta dot times cos alpha over sine alpha. And then I'm going to plug that into the kinetic energy again, just so we can see what that is going to look like. I'm going to move the 1/6 over here. Rho pi r squared h a squared theta dot squared cos squared alpha plus ixx over 2. It's omega squared, and the sine squared alpha will cancel out. So theta dot squared cos squared alpha. It's izz over 2. You still have the cosine squared alpha, but you also have a cotangent squared alpha. Yeah. Which means each of these have a factor of theta dot squared cosine squared. So we can just go ahead and take care of those. So theta dot squared cos squared alpha. It's 1/6 rho pi r squared h a squared plus ixx over 2 ixx over 2 plus izz over 2 cotangent squared alpha. Cool, cool, cool. At this point, it's worth plugging in. No. At this point, it's worth putting alpha in terms of the dimensionality of the cone. Um, Very simply, just alpha equals the arctangent of the radius of the cone divided by 2 times h of the cone. Right? Yes, 2h. So, and then you're taking trig functions of that angle a couple of times. So that means we can simplify. So we're doing cosine alpha, which is cosine arctangent r over 2h. The form of a cosine of an arctangent is something that is known from trigonometry. So you can express it as it's basically 1 over the square root of alpha squared. So 4h squared plus 1. Yeah. And then you also need the cotangent of the arctangent, which all that does is inverts it. So it's 2h over r. Plugging that into the kinetic energy, you're doing theta dot squared. Ooh, big denominator. Theta dot squared divided by r squared over 4h squared plus 1. All of that times 1/6 rho pi r squared h a squared plus ixx over 2 plus izz over 2. And then cotangent squared is going to be 4h squared over r squared. Yeah, okay. Now it's worth plugging in the principal moments of inertia of this guy, and also just noticing that theta dot this whole time was defined by 2 pi over tau. You know, and then so this is a different problem all on its own that I might do at some point. But the principal moment of inertia for the cone is just for ixx, it's rho pi r squared h r squared over 20 plus h squared over 80. And then the izz is rho pi r fourth h over 10. Plugging all of that in and also kind of simplifying the prefactor by multiplying top and bottom by 4h squared. So it's 4h squared times 4 pi squared over tau times r squared plus 4h squared. Right? 1/6 rho pi r squared h a squared plus rho pi r squared h over 2 times r squared over 20 plus h squared over 80 plus, so that's 2h squared over r squared times rho pi r fourth h over 10 pretty exciting stuff, this. Now we just have to simplify. Um, I might be here for a while just simplifying. I might fast forward through this part. I think that's about as simple as it gets, actually. So, there you go, kinetic energy. Uh, let's now just look at. So we need to find the angular momentum uh, components, which you just those are very simply the principal moments of inertia times the angular velocities, right? Uh, so there isn't an Ly because there's no angular velocity in y. Z omega z will have, so omega ended up being theta dot times cosine alpha divided by sine alpha. So it was, for omega x, it was sine alpha. So it's actually just the principal moment of inertia, h r squared over 20 plus h squared over 80 times 2 pi over tau times cosine alpha. Yeah. And then we already found a form for cosine alpha. So it's rho pi r squared h over square root r squared 4h squared plus 1 over tau, and then that stuff. I don't see any point in simplifying that. Then LZ, that was LX. LZ will be rho pi r squared h. No. Rho pi r fourth h over 10 times 2 pi over tau times cosine alpha cotangent alpha. Okay. So that is rho pi squared r fourth h over 5 tau times that junk. Times the other junk, which was 2 pi over 2h over r. Yeah. Again, I don't see any point in simplifying this further. I really don't know what the point of this problem is. It just seems like algebra hell.